Students, can you hear me? Can you hear me, students?
Yes, sir.
Please say something at least.
Yes, sir.
Yes.
Thank you so much. Okay, so in the last class we have seen the voltage reflection diagram, the bounce diagram. Fine. And it was discussed like this was a circuit, if you remember. So the transmission line was terminated with a resistive element, and we observed the transient behavior as well. Fine. So the thing was like this is somewhat is not practical when we are dealing with the at microwave frequencies, because at higher frequencies we cannot ignore the capacitance and inductance. So uh, mainly when you are working at high frequencies with these transmission lines, so you have to deal with the reactive load. Fine. So today we'll be talking about that, how the things will be happening with respect to the reactive load. And from the previous class it is clear to all of us that how we will make the reflection diagram, how we will calculate all these procedural things. Now we are known. Fine. The only thing is that today we'll try to replace this register with capacitive or inductive load, and we'll repeat the same kind of exercise what we performed in a previous class. Okay, so in this class we'll try to learn these things. Okay, so because this is most very critical thing, and we are going to use in coming classes these kind of concepts. Okay, so today we'll see lines with reactive load. Fine. So the thing is like what we have observed so far, that for resistive termination, the incident and reflected wave have same time dependency. Fine. Okay. And for reactive termination, the reflection coefficient is not actually constant, and the transient behavior of the termination should be studied by means of the differential equation. So this is the thing actually we have to perform here actually when we are terminating with the inductor or capacitor or any mixed kind of situation. So what we'll do today, we'll take it step by step. First, we'll analyze that how the things will behave with respect to inductor, and then we'll see with the capacitor, and finally, we can able to visualize that what will happen if the load is purely this complex or mixed or whatever. Correct. So today we'll be talking about only the reactive loads. Fine. So let me just draw the diagram, circuit diagram here. Fine. So this is R naught, and this is V naught, this is plus. And let us connect our transmission line. Fine. This is a transmission line, and let us connect here the inductor. Fine. So this is what? This is Z is equal L. Fine. And this is Z is equal 0. Fine. Let us connect here this transmission line with this source side, and here we'll apply mega switch. Correct. At t is equal 0, this is going to be closed. Fine. It means that t is equal 0. It means that like what we can indicate from this side onwards, this is V1 plus. Fine. And the characteristic impedance we have taken is R0. Here this is L and this is VL. Fine. Okay. Now we'll try to analyze here. We'll try to make the bounce diagram. You can also try the bounce diagram this for this circuit as well. But before that, we'll perform some mathematical derivation here, and we'll try to learn that how the things are dependent with respect to this reactive element. Fine. So let us analyze these things, and the switch is going to close at t is equal 0. So definitely one can find it out V1 plus as R naught over R naught plus R naught. Just simple voltage division rule into V naught. So we have V naught by 2. Okay. And thus this particular V plus is going to travel towards the load. So, and definitely the velocity will be U. 1 upon under root LC. We know these things. Okay. And you can also calculate the time period as L upon U. Fine. This is one time period to travel the length L of the transmission line. So what happens actually at t is greater than and equal to t. So what will happen? This V1 plus will go up to here, then it will bounce back. Okay, and because this is actually the reactive element here, the reflected wave will be function of time. This will be a function of time. So what we can write if let's say if I ask this thing that to find it out the voltage at t is greater than and equal to means at this time, at this moment, the wave will be on the inductor and it is just start to reflected, right? So what we can write actually that if I ask you write VL as a function of t, immediately we can write V1 plus V1 minus is a function of time. Okay, let's say this is equation number 1. Fine. Why this is function of time? Because this is a reactive element like capacitor or inductor. This is charging and discharging phenomena and storing phenomena is happening. Okay, so the thing is reflection coefficient will be also the function of time. So we cannot ignore this fact. Okay. Now, similarly, you can also write I current IL. Fine. It is a function of time. This will be just negative sign and division of R naught, V1 plus over R naught minus V1 minus the function of t divided by R naught. Same thing, just small changes we made here. Now, what we can do actually, because the thing is, one relation we already have from our circuit theory course, if you remember that VL is a function of time, could be written in terms of the inductance. Fine. So L stand for the load, DIL the function of time over dt. This relation we already have. Fine. Now we have 3 equations. We can do some reordering or rearrangement here, and we can reach at the very important conclusion. Fine. So if I say that I have to write the V1 minus as a function of time, fine, in terms of V1 plus R0 and IL, definitely we can do actually. We can do these things. Okay, fine, because we don't want to these things. So if I do this thing, this will be V1 plus minus R0 IL is a function of time. Can we do these things? Yes, because we have this relation V1, VL, these things, IL we have these things, VL we have these things. Fine. Okay, and other things we can write down like that VL is a function of time is equal to 2V1 plus minus R0 IL is a function of time. Fine. it is quite actually clear, because if you know these things, V1 minus is a function of time, you can replace this term and finally you can calculate VL. What we did actually, these things. So we manage from these equations, okay? From these equations we manage that how we can write V1 minus, okay? In terms of V1 plus and IL, these things. Now if you check here, so this equation is in terms of V1 plus, which is a known term, and R0 is a known term, and IL. Right? We need to solve it. We need to solve it, and we can solve. I can give you a hint here that this equation could be utilized to solve these things. Fine. So what we need to do, this is a differential equation. Okay. We need to do some little bit extra here so that this would be in a proper form, and we can calculate. We can guess the solution and all. And finally, we can recall the solution in this equation, and we can write down what will be the VL is a function of time. Fine. So what we can do actually. Okay. So let me draw these things. So what we can write actually. Let's make the circuit with respect to the previous equation. I'm making a circuit actually, because this is just following the KVL. Okay, and this could be rewritten the circuit like this. Okay, this is IL, this is VL, this is LL, this is Z is equal L, and of course this is what will be, this is 2 1 plus. Okay, and this is R0. Remember this equation, VL is a function of time. The last previous equation that's popping here, 2V1 plus minus R0 IL. Better to form the circuit. Can we do? Yes, definitely we can do. Okay, in this form we can write. Okay, so this is what? This is the equivalent circuit at the load end for T is greater than capital T and equal to the capital T. Now, what we can do actually, we can, because we already have one relation which is VL is a function of time is equal to LL DIL is a function of time over dt. Okay. Now the thing is, with these two actually, we can make a very important equation. This is a first order differential equation actually. Okay, so better to write this things like this is actually in IL. So just replace here this VL with this term, and we'll be having a very nice form of this equation. I'm writing here LL DIL is a function of time dt plus R0 IL is a function of time is equal to V1 plus. This is what? This is for T is greater than or equal to. Fine. I did nothing actually. I just rearrange all those things. Fine. So replacing this term with 2V1 plus minus these things. Okay. So this we are bring down in a right hand side, and we written like question like this. Okay. This is what actually. This is the first order differential equation, and we solved many times in our math course. Fine. So what is the tentative solutions? If you recall, so the tentative solution will be in exponential form, and here we can see this is actually differential equation where the unknown is IL. So we can guess the solution here because we already have the idea that what are the different particular solutions for this differential equation. So not going in a detail of that how we will solving this differential equation and all. Well, I'm directly copying the solutions actually what we made in a math class. Okay, so IL is a function of time is equal to V1 plus over R0 1 minus e to the power minus t minus capital T R0 divided by LL. Okay, this is for t is greater than t. Fine. Okay, so this is what, this is the solution. This is the solution for IL is a function of time, correct? Now, we can recheck this equation. How we can recheck? We can put initial and final conditions here and we can recheck. And if I write IL is a function of capital T, what will be the outcome? The outcome will be 0. If you check, okay, T minus T will be 0, this will be equal to e to the power 0, and this complete thing will be 1, and ILT will be 0, right? In a similar way, that IL is a function infinity at the infinity time. Let's say if I'm thinking, so what will happen, that e to the power minus infinity, okay, e to the power infinity. Okay, so better to this thing will be ignoring this term, and this will be v2 v1 plus over r naught. So the final value will be 2 v1 plus over r naught. And this is what actually we can expect actually from this trivial circuit. We already have done the parallel things in a circuit theory course. Fine. So it means that yes, definitely one can use the solution. Now, after having the value of IL, these things, one can also find it out the VL. Fine. Yeah. So what will the VL? The VL is a function of time will be LL DIL is a function of time over dt. Okay, so better to recall the solution LL d of dt 2v1 plus over r naught 1 minus e to the power minus t r naught capital T, sorry, LL. R naught LL. Fine. Now let's differentiate with respect to time, and definitely we'll get some output here. This will be 0 and we have to differentiate with the exponential. So I'm writing the final one. Okay. I hope you can do the intermediate step here. V1 plus e to the power minus t minus capital T r naught by LL. This is for t is greater than or equal capital T. Fine. Now finally we can write the expression for the reflected wave. Can we write? Yes, definitely. Because we have all the things here, and we already have the relation that VL, the function of time, is equal to V1 plus V1 minus is a function of time. Now V1 minus V1 plus, we have already the value VL, we have already expression. So it is quite easy to write V1 minus is a function of time, and this would be 2V1 plus e to the power minus t minus capital T r naught over LL half. Okay, and this travel in what direction? This is minus z direction. This is reflected. Fine. Now the thing is, if I ask you to plot these things, okay, how will you do these things? Because we have the sufficient background, the plotting, all those things. So definitely one can plot these things easily. Correct. So let us plot this. So first, I'm drawing here IL to the function of L comma T. Fine? Because at the load point we are observing the thing, so better to replace Z with L to the function of time. Okay. So we already have IL. Fine? We have already solved for the IL. Okay, so we need to run the code. Okay, what we are going to make over the MATLAB or any other software. Okay, so you need to change with respect to time. You can observe the thing, the curve will be like this. And this is what, this will approach to the final value, and the final value we already have seen. This is 2v1 plus over r0. Okay, this is capital T. This point is capital T. Fine. Now, next is we can draw the VL. VL we already derived the expression. VL is a function of L comma T with respect to time. Okay, so that VL we can easily do these things because the expression was 2v1 plus into e to the power minus t minus capital T r naught by ln. So definitely at below time period t actually. Okay, so what will happen? This will be almost zero actually. Correct. This will be almost zero because the thing is the wave is not going to reach actually up to that point. Fine. So we can make it zero, and then after the things will be sudden change will be there because it will get means charges actually, and gradually the things will be discharging. Correct. So if I draw these things, better actually we can definitely visualize this exponential and all the things because we have sufficient background to draw the graph and all. But better to make a code. This is 1 or 2 line MATLAB code, and you please run over the MATLAB, and you will get the clear cut picture. Fine. So if I draw these things, so this will be capital T. So up to this point, this will be zero, and after that, sudden change, and then gradually down. Right. This is what this will attain the value of the final value, which is 2v1 plus. This is one thing. I should write actually the expression here, so you can correlate. Just a minute. So IL is a function of time will be 2v1 plus over r naught 1 minus e to the power minus t minus capital T r naught LL. Fine. And here this would be VL, the function of time is equal to v1 plus e to the power minus t minus capital T r naught by. Fine. So one can easily actually visualize that how the graph will look like. Means tentative graph you can plot. But if you require a specific value, definitely you have to write a code over the MATLAB and you need to draw it. Okay. Now, can we plot the V1 minus? Yes, of course we can do also. Okay. So what is the V1 minus? What is the V1 minus? V1 minus we have already seen. The expression for V1 minus is a function of time is equal to V1 plus e to the power minus small t minus capital T r naught by LL minus half. I have given these things. Wait. Yes, I have given. Okay, these things. So now we can plot it. Fine. So if you're good enough to visualize the thing, definitely you can do rough graph. Okay, so based on that thing, I'm providing you the same. So this will be like this. This is just a minute. What we can do actually. This one and this one. We'll plot like this. So this is T, and this is V1 minus the function of time. Now, we need to mark here these things. So, what will happen that initially up to the time period capital T, this will be 0, and thereafter there will be one shoot up is there. and there is 1 minus 1 by 2. So it will start gradually going down and reaches to the value of minus V1. This point actually is minus V1 minus, fine. Okay. Similar way, you can also plot V is a function of Z comma T at specific time, let's say. Fine. So how will do? You have to make the bounce diagram and all. Correct. I just drawn here for time period T and after some time. Correct. Now this is means you have to do from your own that how to make its bounce diagram. Correct. I'm leaving over you these things. I'll give some problem. Okay, and I'm expecting that you can manage it because almost the things are same. And you have to find it out what is the specific application of the same. So this would be, what is that? The function of Z, and this is at some particular specific location. This is going in this side. Okay, reflecting back. Better to run the simulation so you will feel these things. Okay, this is V1 plus, and this is 2V1 plus. Fine. So this is all about these things. Okay, and other thing is that we can also find the same thing lines with capacitive load. So almost the phenomena what we studied for the capacitor, it is just somewhat parallel, or I would say opposite actually, with the capacitor. So a little bit change will be here, but the solution and all the things will remain means going in a right that same direction what we just have for the inductor. So we are placing a capacitor, let's say CL, and this is VL, this is R0. We are putting a switch at t is equal 0 is going to be on, and this is R0, and this is V0. Fine. So these are all the things that I'm taking similarly what we did in our previous socket. So here also we can make it VL is a function of time, which is V1 plus, and this will be again V1 minus as a function of time, because this is again a reactive element. Okay, there will be charging and discharging, so the reflected wave will be the function of time. It is not like that all the time we are getting the same reflected, because reflection coefficient will also is a function of time. It depends over the how the capacitor is going to charge and discharge. Okay, so in the same way you can write things here also. IL is a function of time, V1 plus V1 minus still. And the Vn, the function of time, you can write 2V1. I'm just rearranging the above list equation. 2V1 plus minus R0 IL is a function of time. Now, everyone is knowing about for the capacitor that there is a relation IL is a function of time is CL dVL by dt. Fine, these things we are knowing. So these are some basic things. Now, based on that, we can write down one very important equation. That is the first order differential equation, and we can solve for VLT. The same thing what we perform ILT there. Here, this will be VLT. CL dVL is a function of time dt plus 1 upon R0 VL is a function of time is equal to upon R0 V1 plus. This is at t is greater than or equal capital T. Here the V1 plus is V0 by 2 from voltage division rule. Now this equation is very well known, and the solution could be written in the same manner what we have seen in a previous circuit, which is 2V1 plus 1 minus e to the power minus t capital T and R0 CL. Remember this is time constant, and here if you find out the VL at capital T, this is going to be 0 because this is a DC. Okay, So these things, okay, and after settling down or at high this thing infinity, this will be 2v1 plus. Fine. So in a similar way, we can perform here also these things that we can find it out these things and IL this IL can be find it out because VL we already have. So IL will be what? The function of time will be CL d VL over dt. Fine. Now we need to differentiate that solution, and we will be having 2v1 plus. So almost the same things, but little bit change here in a capacitor. Due to this capacitor, we have different current and voltage. But mathematically, this is a dual. I would say this is a dual. Okay, the parameter we are going to get is dual. And VL, the function of time, will be, we have seen that V1 plus V1 minus is a function of, now here we can find it out the reflected wave. The reflected wave will be VL is a function of time minus V1 plus. Fine. So if you rearrange all those things, okay, so you will be having 2V1 plus a half minus e to the power minus t minus capital T R naught CL, fine, from T is equal to T. Okay. Now you can plot certain things here. Okay. So after having, because we already have seen this mathematical similar mathematical form. Okay. So just quickly draw VLT. I believe you can guess now because last time we have seen this thing, this previous circuit. This will be like this. It will be 0, and then it will start, and it is going to settle down at final value, and the final value is 2v1 plus. Fine. In a similar way, you can also plot the reflected wave, which is v1 minus is a function of L, means at the load actually, sorry, at the load and time, and this would be like this. At time t, this will be 0, and after that there will be negative dip, and then after it is like this. So this is what, this is going to settle down at V1 plus as per the formula, as per the relation we have seen. And this is what, this is V1 plus minus. Okay. Okay. And other things you can also draw, like with respect to a particular time. Okay. So this will be, let's mark 2V1 plus, this is V1 plus, and the y-axis is v is a function of z, comma t1, specific time. I'm talking about the specific time. So this will be v1 plus v1 minus is a function of time. Fine. Now if you draw it, this thing, so it will be like this. There will be a pulse kind of things up to z1 at any location, let's say, and after that it will be start exponentially increasing like this, and up to L. This is, let's say, L. Correct. It is going back towards the source side. Okay. So here T1 is, you can say 2T minus Z1 over U. Fine. So in this way, we can plot certain things, and we can observe that how the things will be, how look like. Now the thing is, that is fine that in a practical scenario, we are going to get this situation that the load will be always the complex kind of things. It will be not resistive. So the thing is, this will be providing us idea that if, let's say, somewhere some different load or different things are there, so at least we can guess that what kind of load is there. Okay, because for the capacitive and for inductive and for resistive, what kind of the reflected wave would be. Based on that, we can guess actually that this will be the capacitive inductive, and this is really very helpful actually, because somewhere at some, let's say 2 or 3 kilometer, we have a certain cut capacitive or these things, or mismatch. So one can say actually this is capacitive and this is an inductive kind of things. So TDR is actually one of the instrument where we are using this concept. So this is all about from my side. Correct. If you have any questions.